Hello everyone and welcome to Rebel Way. My name is Andrew Sutherland and today we're going to be continuing our earthquake effects with this second part. And in the first tutorial we created, the majority of it was some RBD destruction, and I also showed our own technique for creating a fake RBD sim for some ground fracturing. And when I say fake RBD, it looks like an RBD sim, but it's in fact all just transforming pieces at SOP level. And today we're going to continue with a little bit of RBD with this. Let me just press F on my keyboard. With this curb, we're going to break this apart and sim that. And then we're going to fracture this grass and ground. And we're going to loop over these pieces. And we're going to make some of them gray so it looks like there's some rocks inside. And then we're going to transfer this color onto some particles. And we're going to do a particle simulation with some grain clumping, and that's going to be our soil. And from there we're also going to prepare this tree. So we've got this tree, we're going to create a wire version of that like this, and we're going to then simulate our main sim, which is going to be just with this tree trunk. And then we're going to use the position of this tree trunk to transform that wire one. So if I come here and I template our actual sim, so this is our actual sim with just the tree trunk, and I'm just going to template our wire version. And as you can see here, if I flipbook this, so as you can see now, our wire tree is being copied and transformed into the same position as our tree trunk, which has been run through the RBD simulation. And from there we can create some secondary animation on this by feeding this wireframe into a wire solver. So from there we take that, we're outputting this tree. This is our transforming with our RBD simulation, and we're going to feed that into a wire solver. And then from the result of that, you can now see this is bending and moving and got some secondary animation. And from there we can transform and copy our high-res tree. And once we use our deform points, you can see our high-res tree now has all that secondary animation to it. And then of course this is just our collisions and smoke elements, and layering things up nicely. So that is what we're going to be doing in this tutorial. So we'll jump into the nitty-gritty details now, and thanks for watching. Okay, so in this video we're going to be taking a look at creating the tree. And we're going to be using a wire solver here. So what I've got here is I've got our tree geometry, and I've got our wireframe. And on our wireframe, I'm just keeping the color, the normals, the position, and this attribute called width. And this width is quite handy inside the wire solver. And in the final project, when we jump into the overview, I'm going to show you how we can generate this width attribute if you don't have it. But for now, to keep this simple, we've got these wires with a width attribute. So let's just put down a null, and let's call this out wires, and let's put down a dot network. If we dive inside, we're going to put down a wire solver, a wire object, and let's just plug this up for now, and let's put it at a gravity. On our wire object we want that SOP path, so let's just copy this, and under visualization we can enable that width. So this is what our width attribute is looking like. If we were to come out here and put down a polywire, and we were to type in at width, yeah, it's very fat, so let's multiply it down by 0.01, increase it. Cool. So that's our width attribute. Let's just press play to see what we get, and you can see it's falling down, so we need to put down a ground plane. Let's add in a merge here. Let's add in a ground plane. Swap these positions. And as you can see, this just falls apart and all our branches fall off. And I'm just going to enable this so it plays back in real time. And in order to fix our branches from falling off, we need to fuse these points. So let's just add a fuse. Let's pin this to our viewport so we view it here. And as you can see, our branches are now at least sticking to our tree trunk. So we're in the right direction. And let's dive back inside and let's change our settings on here a bit. So let's come over to material and let's multiply this width. Let's increase this to 4000 and let's increase this K angular. You can see this is an attribute called K angular. I'm mentioning it now because in the final project we actually set this on a wrangle, but for now we can actually just multiply it up here, and this is going to make our tree stiffer. And let's add some dampening. Cool. As you can see, our tree is obviously just falling over. So in order to stop that, what we can do, let's put down a group. I'm going to unpin this. I'm going to say group. Let me set this to points. And I'm going to say keep bounding region. And let's just increase the size here. Something like that. And let's put down a wrangle. And we're going to run over that group. And we're going to say I at pin to animation equals 1. And now if we dive inside, you can see that these are now a pin, like working like a pin constraint. So cool. Okay, so I'm back and I've just made a few changes. Added a clip here just so that I can clip off the roots. Just didn't want to include those for now. Same thing to my geometry here. And coming over here on my wireframe, I've changed these settings to this and under physical, and that's about it. And from there, I've got a DOP import, and I'm reading in this DOP network, and I'm just importing the wire object. So you could just do this. And from there, we're going to cache this out to disk. So let's cache. And then I'm using this point deform to point deform our geometry. So here's our tree. Like I said, I just clipped the bottom, and this node requires our geometry to deform a rest position. So for that, I'm just freezing this on frame 1 and our deforming geometry. And when we point deform that, we get our final sim. Cool. And this is essentially what we're going to use in the final project. And if you take a look at the advanced magical effects, Hunter shows a bit more of a sophisticated way of doing things, as well as our advanced studio workflows. There's a very advanced approach to tree destruction. But this is just, like I said, the simplest way we can do things. You can see how simple this little network is. And of course, we're going to generate a lot more of these attributes from scratch in the final project. But for now, I just wanted to show the simplest way possible to do a wire simulation for our tree. We're going to jump into the final scene now and pick up where we left off on the last tutorial. I believe we've still got some RBD of the curb to cover, some grains, and like I showed obviously here, we're going to take a look at a bit more in depth this tree and wire solver. Cool, so I'll see you in the final project. If we dive into the Houdini file, this is where we sort of left off. And if we come back down here to this curb, you can see we're importing that geometry. And here we're just isolating this part here. So if we press F on our keyboard, we can frame up. And like we did before, we're just running a group for the edges. That way we can remesh and retain those edges. I showed this in the last tutorial, but as you can see, if you turn this off, we're losing the shape of our geometry. And we have an alt now. Over here, we're going to scatter some points. And here we're just setting the value to 0, so they sit on the floor. We're fusing those points so that if there are any points that are close to each other, they just snap into one position. And here we're just adding some random rotation to those points. And that's because we're going to copy this grid onto those points, and we're going to use these to cut up our curb. So if we come over here, you can see we've got this, and if we were to untick this, we no longer have that rotation. So we just have the rotation along the wire here. From there, we're copying this to those points, and you get the idea. If we come over back here, we come over to the curb, and here we've got a peak. And we're just using that to group. We're promoting that group to the primitives. We're blasting this, subdividing this, distorting it even further. And then we're using this as a subtract. We're going to set our groups for the outside. We're going to put down a normal, and then we're going to fix those normals on the outside. So the inside of a normal and the outside of a normal. And here we're creating a name, and we're calling it curb. And then we're going to pack those primitives as per usual. And if we want to just see an exploded view, you can see our pieces. So this is actually quite simple stuff. You know, there's a few extra things in here looping over, and a lot of it's not really necessary, but this is the final project, and you can see how exactly it was done. Here we're creating a group again, and here's our exploded view once again. And from here we're going to make our constraints. So as per usual, we're saying adjacent pieces from points, and once again we're going to uniqueify those points. Here we're deleting some of them, and then we're using this primitive node to scale down to 0. So these are all just our points. And here we're just setting the name for those constraints. So when we send this to DOPS, we can use this name to specify the strength and the breaking rules. Here we're going to put an null for out, and that's it for our curb. We've got some more constraints. Here we're unpacking the pieces. Here we have our outside unpacking. We're merging these two together. And once again, we're going to connect adjacent pieces from points. Now this node is the same thing that we used in the last tutorial, and we're using this to compare the names of the primitives, and here it's saying if they are the same, then we're going to split. So if we take a look at that, so now we can isolate this, and if we were to inverse this, we would get the inverse. So I did show this in the previous tutorial, and I showed how a little simpler way than just doing it than this. If we come back up here, where is it? Here. So we have our pieces. In this case, we're dealing them below. We're connecting adjacent pieces. And here, so this connect adjacent pieces is going to delete our original name because we've got two names on here. We've got the name and we've got the origin name. And once we connect pieces, all we have is the name again, because this is what this node does. It's going to save over that. So all we need to do is transfer that name, origin name again. And as you can see, now we have the name and the origin name, but this is a primitive and this is a point. So we want to promote these from primitive to point. So now we've just got the name and the origin name on the point. And then we're just using this code to run over the primitives, compare them, and if they're not the same, we're going to delete. So for instance, so if we put down a color, let me show this, and we take a look at random from attribute. These are primitives currently, and we want to take a look at the name. Cool. So now we can see this is our origin pieces and our name. So what this code is doing is it's looking at these pieces, right? And it's saying, okay, this piece, all these pieces have the same name. But this piece and this piece don't have the same name. So where they connect, we're going to remove those primitives. And as you can see that here. So if we take a look here, let me make another color node. And here, origin name. So where these are the same, we're going to keep. And where these are not the same, we're going to delete. And so now if we take a look at this here, you can see that those pieces are deleted. So that is what that code is doing. And we're doing the exact same thing. Where was it? Here. It's just that we're doing it purely in the wrangle. This is promoting the points to the primitives, and we're looking at the name and we're comparing them, and then we're splitting them if they're not the same. And if we were to put the exclamation here, so if they are the same here, we're removing them, and if not, we're doing the opposite. Hope that makes sense, and like I said, I did cover this in the previous tutorial. From here, we're just reducing points again based on a selection. Here we're uniquefying the points, and once again scaling down to 0 on the primitives. That way we have our constraints, but they are all as points, and this is what we need for the DOP. Here once again we're going to set our constraint names, and that's it for our constraints here. Next up, we're going to take a look at the soil, and so we're importing our geometry. This blast isn't doing anything, and here we've got this connectivity node, and that's part of this for each connected piece. So if you were to put down a for each connected piece, you'll see it gives us this loop, and it's creating a class attribute on these primitives. So that is what we've got here, and we're basically just going to run over each of these pieces, and we just have two. We have a top layer and a bottom layer, and here we're creating a density by coming over to this ISO offset, and just if you change this to fog, it gives us a VDB version. And we're just creating a noise by taking adding a AA noise, fitting those values between 0.84 and 1, just so that, you know, there's not nothing. So there's always going to be some. It's just in this part it's going to be denser, and then we're saving that out as the density. That way we can scatter points in that density. Where it's high density, we're going to get more points, and where it's low density, we're going to get less. And then we can just Voronoi fracture this. It's going to give us our fracture, and then once we loop over this, it's going to do it on all our pieces. So like I said, in this case, it's just the 2 pieces anyway. So here we can assemble and we can check out the exploded view. These are all our pieces. And here we're labeling that top part and we're calling that top ground. And here we're setting a color attribute. And this is just based on the wire distance. So if we take a look at this, we take the position, we take the wire per component, we put that into a fit, and we feed that into a ramp. And then we export that as color. And that's going to give us this color. From there, we're going to promote this color from the points to the primitives. And here, this code is basically going to run over our pieces and it's going to select some random pieces. And then it's going to set a gray value on some of them. So some of these are going to look like rocks or gravel in our ground. So that's the purpose of that. Here we're UV unwrapping, so we've got UVs on our geometry. And on our top layer, we're going to set this green color for the grass. And we're going to save this out to disk. From there, you know the drill, same as per usual. We're going to import our geometry. We're going to assemble. We're going to delete the top part. And on this side, we're going to keep the top part. And then we're just going to put down a null. So we can read this into our simulations. And then this is just a packed version. So if we come over here and we've got ticked on pack primitives. Cool. So next up, we just need to make the constraints. And we also have a tree. So where is my tree? Let's take a look at these constraints after taking a look at the tree. So just pressing F on my keyboard, I can frame up. And you can see we're reading in our tree here. So next up, we're going to take a look at the constraints. And I've just come here and you can see where we're bringing in that pack geometry. Here we're just unpacking it. And here we'll take a look at the tree later, but we've isolated just the tree trunk and the roots. We're unpacking that, we're merging this together, and then we're running our adjacent pieces from surface points. And this is going to give us, our constraints. And here we're looking at just the pieces that connect from our tree trunk to our ground using our code again. And here we're setting the constraint names. And here I think this is just our tree. Here it's just the roots. This is the connection with our curb. Oh, and here we're setting some clusters, but we're doing this slightly differently than having, before we were looking at those clusters where we had 2 different names. And in this one, we're creating the clusters using a Voronoi noise. So we're taking our position, we're feeding this into a noise, we're adding that, and then going into this Voronoi pattern, and then we're exporting this as seed, and we're visualizing it as random colors by putting it into this random and then out to color. So let me just take a look at that. Yeah, and as you see, if you change the size, we're going to change the size of our clusters. So that's what we've got there. Here we're faceting unique 5 points and giving a name. Here we've got our bottom part and our top part, connecting those, and now just using a constraint to connect the top part and the bottom part. Here's just our bottom part, the clusters. Here we're separating, so we've using this over the instead of the name, we're using the seed. Giving it a name. Here we're using the inverse, giving this a name. Our top part, clustering with the seed, removing that, doing the opposite on this side, giving this a name, merging it, and then all together, these are all our constraints. And then lastly, we're just connecting to our curb. Cool. And from there, we're going to take a look at our tree. So at the beginning of this tutorial, I showed how to do a YSM for our tree, and we imported the geometry, and we also imported a skeleton version of our tree. I believe SpeedTree does give us a skeleton for our tree, but in case you don't have one, we're going to take a look at how that was created here. So we're just transforming our tree into position, and here we're blasting our twigs, our branches, our tree trunk, and our roots. And what we're going to do is we're fusing these together. So we're just making sure that this is clean geometry, and here we're going to run over each connected piece, and we're going to scatter points. So pressing F on my keyboard, we can frame up, and you can see here we've just got one of the branches, and we're scattering points all along it. Here, from there, we're going to connect adjacent points, and we're using the smooth node to shrink these points, or these now primitives, down inside. And from there, we can use a fuse to snap all the points together where they're close, and that's going to leave us with just this one nice wire or constraint. And when we loop over all of that, it's going to give us a nice skeleton for all our branches, as you can see here. And here I'm just visualizing, I'm just giving it a color, and I'm computing the rest length here. And here we're giving this the name twigs. And we're going to do that for everything here. So these are our branches. This is our tree trunk. And this should be our roots. Cool. And we merge that all together, and we've got this really nice skeleton that we've generated just from the geometry. But we do have a problem. We can see that these branches are not quite connecting to each other. And as you saw, you know, if we were to obviously send this to a wire solver, Vellum solver, or an RBD solver, they're all going to fall apart. So we need to look at connecting those pieces. Here we're just resampling this, so you can see we've got these points, and we want to create an even distribution. So we're doing that. We're fusing these to reduce the amount of points, but they're now evenly spaced, and we're going to loop that over our tree. From here we're just going to loop over each section individually. So let's take a look at this one. And once again, for each connected piece, and we have our tree trunk over here. And what this node is going to do is it's going to look at the closest point to our tree trunk, and it's going to snap it. You can see, let's template this. It's going to snap that point onto our tree trunk. So before and after. It's also going to create a point on our tree trunk. Let's loop that over, and as you can see, before and after. I've put some notes here on these nodes if you want to, if you're not sure of things, but basically this is what it's doing. It's just raying that point based on its closest neighbor. Cool. And here what we're going to do is we're going to create that that width attribute. Let's take a look here. Yeah, so what this is doing is it's saying how close are these points to the origin of our scene, and the closer they are, we're going to map a value of 0, and all the way up here, based on its distance, is going to give it a value. So here I'm just putting a color node so I can visualize that width now. And as you can see, I got these values by just looking at my geometry spreadsheet. So if I come up to geometry spreadsheet and I look for width, you can see it goes between 0.11, so let's just enter that in, and maximum value is 4.35, 4.32 in this case. Come back here, and this is now evenly mapped. And what we can do is we can actually use this attribute promote to calculate the maximum of this width. So this maximum is now going to capture this value here, and then we're going to promote that as an attribute max width from detail to point. So if we come look over at our geometry spreadsheet, and now you're going to see an attribute called width max, and it's going to have a value of 4.32. So max width, you can see 4.35. That's the maximum. That's the maximum of our width, and we're just doing this so that we can procedurally manipulate our data. So we don't have to look up what it is every time. I was doing that to just fit this into a color range, but we don't need to do that. We can use this to capture that width and then save it as an attribute, and then using this we can use that max attribute to normalize the width attribute. So what we're saying is that we want to take the width, and we want to fit it between 0 and its maximum value, and store it from 1 to 0.1. So normally if we wanted to just normalize this, it would be from 0 here to 1, but we're actually negating it, and then we're multiplying it with the slider. And you know, we're using the slider just so we can control this width. So if I were to let's put down a polywire, and in the width we could say at width, and it's very thick, so let's just multiply it down. You can see we're giving some thickness to this. Let's just change our background color. So you can now see that this width is driving that, but we're using this multiply, and we're multiplying it up here just for our wire solver. From here we're computing a rest length. We're fusing points, and here we're setting that K angular value to 10. This is just like a multiplier, but we're doing it on our geometry here. And the same goes for all our other pieces. So here's our roots, our branches, our twigs. Merge that all together. Here we're just deleting this top part. I'm not so sure why, but we're deleting that, cleaning up some things. And here we're selecting just these bottom points, and we're saying glue to animation. And like I showed in the beginning, that means that this part is just going to move with our RBD sim. It's not going to be affected by the wire solver. So these are the points that we're isolating. You can see them down here. Let's press F on our keyboard, and let's press D, it changes back to dark. So those are points that we're selecting to be inactive in our sim. And here we're temporarily setting this anchor ID and original point as -1. We're setting rest points as the point numbers. I'm not 100% sure why this is necessary. I didn't seem to need this in my wire sim, but you know, we have some extra constraints here. Here we're looping over all our pieces, and we're trying to see which is the anchor point. So like this will be the anchor point, this will be the anchor point, this will be an anchor point, and that's just looking at this and determining which is 0 and which is 1. And you know, if we were to, and like I said, I'm not so sure why this was totally necessary, because when I ran a wire solver, it seemed to work fine without this. but this is what's happening here. And we're just setting names, constraint names, and then putting a null out. Cool. Here, if we come over to our tree, this is just preparing our high-res geometry, and we're just modifying things a little bit, peaking things, and adding some noise to our tree trunk, as you can see, subdividing it, peaking it again, you know, just making our geometry a little bit better. Here we're adding our materials, computing the normals, and here's our leaves, merging those all together and saving this out as our high res. Here we're just transforming our tree into place. So this is at the origin, but we don't actually want it at the origin. We want it based on this point here. If you can see there's a point. So we're just using a copy to points to move our tree into the correct place. Attribute delete, and we're deleting everything but our branch, our tree trunk. And this is what we're going to use in the RBD sim. So we're going to fracture it based on these points. Again, as per normal, we're going to assemble and pack and call this group tree, and we can add this to our RBD system. So we're going to sim just the trunk with our RBD system, and then we're going to copy the wireframe from, then we're going to copy our wireframe tree onto this tree trunk, and from there we're going to run that wire simulation. So that is our tree covered. I think that's everything. We obviously need to just dive into our main simulation here, and you can see I've added that tree and our curb and our constraints, and then we just run the sim like we did last time, and that's going to give us this result. Cool, so here we can see our final RBD sim with our ground, our curb, our ground with the gravel and some grass, and our tree trunk. And like I said, we're going to look at copying our wireframe tree to this tree trunk and simulating that wire sim that we showed at the beginning of the tutorial. And then we add that all together, and we've got our tree and our thing. And the only thing that's really missing here is now we're going to run a particle simulation, like a debris, for all these pieces that we see of the gravel. And then we're going to add some grain control to our particle sim and get some nice clumping and some soil looking simulations. And we're going to add that, and of course, as always, some smoke, and we should have a pretty good looking sim. So I think next we'll just go over the overview of adding the wire simulation to this, and in the next tutorial I'll cover the grains. Cool. So next up we're going to take a look at our wireframe for our tree, and all we're doing is we're importing our ground destruction. We're blasting everything but the tree. We're unpacking that. We're creating a rest version with a time frozen on frame 1. And what we're going to do is we're just going to point deform our tree. So here we're importing the position of the position of our tree, because obviously, our tree was prepared at the origin of our scene, but it actually needs to be here. So we just got our tree that's at the origin, and we're copying that into place. And then we're going to use a point deform to deform our wireframe with our sim. So if we were to do that and then template our ground destruction, well, let's look at our ground destruction and rather template our tree. So you can see now our tree is deforming nicely with our RBD sim. But we just want to add some secondary animation to this, and for that we're going to use our wire solver setup. So from there we can just put an out tree animation, again copying our tree into place, and we're deforming this with our YSIM. It's pretty much the exact same setup. I think the only difference here is those are settings. I think everything is pretty much the same. We do have an extra layer of constraints in this version, but like I showed at the beginning of the tutorial, it's really not necessary. You could just use the setup that I created at the beginning. And with that cached to disk and transformed, let's put a merge here. So I've just generated this flipbook, and you can see I'm merging in our destruction. I'm just blasting away the tree, and I'm merging that in with our YSIM, just so that we can view these two together, and we get a pretty cool result. We've got some jittering at the top here. It's not perfect, but we can just either blend shape that or time remap, and we'll take a look at at all those things in the final render. Before we close this tutorial, let's take a look at the grain setup, and it's fairly simple. It's basically just like our debris simulation using this pop network, but what we can do is we can add this pop grains node, and what that's going to do is it's going to mean that our particles now are aware of each other. So in a particle simulation, there's no sort of collision detection with each particle, but when you add this pop grains, this essentially makes it like a grain simulation where particles now are aware of each other, and we can introduce some clumping. So if we jump back out here, you can see we're reading in our RBD simulation, and let's delete everything except for our curb here, and this is basically our ground, and we're going to use that handy debris source once again. So I've just temporarily cached this out so we can scrub through it easily, and you can see this is our debris source, and what we're doing is we're unpacking this geometry here, and we're promoting the color from primitive to point, and then we're using this to transfer the color onto all our points here. So now we've got this debris source with colors on it, and from there we're just normalizing the velocity, so fitting it between 0 and 1. We're setting a p-scale between 0.05 and 0.1, and then we're just cleaning up our attributes and saving this out to disk. From there we have a null, and then we have this pop network. So diving inside our pop network, and we can see that it's basically all the usual suspects: our source to bring in the data, our pop object, our pop solver, gravity, and our collisions. But the unusual thing, or thing that makes a difference here, is that we have this pop grains node added. We also have some pop drag, just to provide some air resistance. What's cool about this is that you can just add this pop grains node to any pop network, and we're going to now have a lot more complicated behavior. In a standard pop simulation, the particles are not aware of each other. They're just points, and they're not colliding with each other. They are essentially unaware of any other points. But once you add this pop grains node, that behavior changes. The particles now are colliding with each other, and when they fall on the ground, they sort of stack up. So what I've done here quickly, I've just added a delete node, so I can delete my source. So here's my source, and I just wanted to illustrate this quickly. So I put down a delete by bounding region, so I can just select some of those points, and I've ran a second sim, this time without the pop grains node. If we were to take a look and compare this result, you can see that these particles are just sitting flat on top of each other. So this is colliding with our debris nicely, but once it hits the floor, it essentially is a perfectly flat result. Whereas if we compare that to our grains, you can see how this is building up on top of each other like you would expect soil or ground. And so that's why we're adding this pop grains node. And if we were to just take a look at these settings, this is what it's basically just a very simple setup. And we're not really doing anything fancy in this case. What you could do is, if you were to do something differently, we could introduce clumping and get a result like this, but without our RBD system. So in this case, we're just using this as like a particle effect to sit on top of these pieces and fill in the gaps. But you could get a similar result using just the pop grains node. But in order to do that, you would have to take this geometry and create a uniform distribution of points. So you could say like points from volume, and you can see this is creating a uniform distribution of points throughout our geometry. And this is what the pop grains needs to do our more complicated clumping setups. And I think we will explore that in a future tutorial, perhaps the next one. But for now, we're just using our debris source, and we're just going to feed that in, and we're just going to use this to make sure that our points are colliding with each other. So these are overall settings. And if you want to enable all the features that this node has to offer, you have to turn this OpenCL off. And you need to be, you often need to increase these sub-steps. Pops and grains can be a little bit unstable, so you want to increase these sub-steps to something like 100 or even 200. And you might want to also turn your gravity down, because if you have gravity is too high and you don't have enough iterations or sub-steps, you might get some jumping in your particles. Another way to prevent another way to prevent the particles from jumping around is you could come to this collision behavior, and you could change this to die or stick or stop on the collisions. But in this case, we can't do that because our collisions are flying up in the air, and we have all these debris pieces. And so if our particles were to collide with that, they're just going to stick with that, or they're going to stop, and it doesn't give us the behavior we want. So in this case, all we need is this very simple setup from the pops grains, and we can take a look at that result here. And like I said, the clumping that we see here is mainly just the layering up of particles on our RBD pieces. So I think this is a good place to sign off for now, and I will see you next time. And please consider liking, subscribing, commenting, all those things. It'll help with the algorithms, and I'll see you next time. Thanks. Bye. Hello everyone, welcome back. I just realized that the grass setup was missing from the original scene, so I've just recreated that, and we're going to take a look at that quick. So what I'm doing here is I'm reading in our simulation, our RBD sim, blasting and unpacking everything that we don't need. So we just need the dirt, and we've got this top layer of grass. And here what I'm going to do is I'm isolating just the top part, and I'm using this group node based on its normal. So this has all our top faces have a normal, and I want to isolate them based on their upward vector. So using this to just isolate the top parts, and then I can delete everything that isn't a top part. And then what I'm going to do is I'm just going to scatter points onto this geometry, and I'm doing this 3 times because what I'm doing is I'm preparing this attribute called PID. And we're feeding the points in here, we're randomizing those, and we're fitting those values between 0 and 2. So 0, 1, and 2, and then we're exporting that as PID. And from there, what we can do is we can take some geometry. So we've got this tuft of grass, this one, and this one, 3 different instances. And we're going to assign that PID value to each one of these. So this one's going to be 0, this one's going to be 1, and this one's going to be 2. And then what we're doing is we're basically copying those points we're copying the geometry onto those points, and it's copying based on its particle ID. So if a point number has 0, then it's going to get this one. If it's got a value of 1, then it's going to get this one. And if it's a value of 2, then it's going to get this one. And this, we're just randomizing the p-scale here. And we're using this to randomize the orientation. So that is really it. But you're probably wondering, okay, but how do we now deform that with our sim? And we've already been doing that throughout this tutorial, and that's with this point deform. So here we have our points that we want to deform. Here we're reading in our simulation. We need a rest version, so for that I'm just going to time freeze this so it's got no movement, and this one is our simulation. As you can see, this is our sim, and then once we point deform those points with our sim, our points are going to inherit that animation. And the only thing that you want to do here is turn down this radius size to 0. With this turned up, you're going to get some weird stretching, and since we're just deforming points, just turn this radius all the way down to 0, and then from there we can copy our grass onto those points. Apply a shader, and we're good to go. You can see this is called airship, so it should be called grass. I literally copy and pasted this from a previous tutorial that we already made, and that's on it was a Star Wars effect for lightning, and we had some spaceships and debris, and we used this exact same technique for that. And you could use this for grass, and you can use this for the debris system. So explore this very, very powerful technique. Cool. Hope you enjoyed this. Please like, comment, subscribe, all that stuff helps with algorithms, and I'll see you in the next one.